All right. Well, our next topic is osmosis. And in osmosis, we can have some particle, usually a solvent, that will pass through a semi-permeable membrane, but the solute particles will not pass through. All right. So usually our solvent is going to be water, and our solute is going to be some other substance like an ionic compound or glucose or sucrose or some other much larger molecule. All right. So first, let's look at the concept of osmotic pressure. Why we call it osmotic pressure. So down here on the left, on the left side of this U-shaped tube, on the left side of this, we've got a pure solvent. In between, we've got a semi-permeable membrane. And on the right side, we've got an impure solution. So we've got our solvent plus some solute. Well, there's going to be a higher osmotic pressure on this side because of that solute. What we'll find is since the solvent particles can go through, but the solute particles cannot, generally speaking, what we'll find is that those solutions are going to drive to get to the same concentration. So solvent particles will push to the right, so we'll have solvent particles going to the right, but we won't have as many going back to the left. So we're going to have a much bigger flow of those particles going. Well, that is going to continue to occur until one of two things happens. One, it is possible that you could get the same concentrations, although if you started with pure solvent over here, that wouldn't quite work. But it'll get to the same concentration, or we'll get to the point where there's a big enough difference in the pressure because of the height of this column to stop the flow. Well, that height is called the osmotic pressure. Furthermore, if you forced it so that they went back to the same level, the amount of pressure that you would have to apply here to keep it from flowing is called the osmotic pressure. And that's what we mean by that this side has an osmotic pressure. So we'll find that the solvent will flow from the area of high solvent concentration to low solvent concentration. Now, that's a little bit backwards because normally when we think of concentration, we don't think of solvent concentration, we think of solute concentration. So it'll go from lower solute concentration to higher solute concentration. But it does go from higher solvent concentration to lower solvent concentration. Okay, well, calculating the osmotic pressure is relatively easy, and it looks just like an equation that we've seen many, many times, which is it looks just like the ideal gas law. Instead of P, we're going to use pi, and it's uppercase pi, as our osmotic pressure is equal to N over V times RT. But again, that looks just like our ideal gas law. So we're quite familiar with this. We have seen this many, many times. Well, if we want the number of moles divided by the volume, that is also equal to the concentration in molarity. So we can write this equation in either of these two manners. So I'm going to write that as that pi, uppercase pi, is equal to N over V times RT. And we'll use that here in just a few minutes. Now, as far as osmotic pressure goes, there are a couple of different types of solutions that we can refer to when we're talking about osmotic pressure. One is called an isotonic solution, and that's where you have the same osmotic pressure inside or on one side of a semi-permeable membrane as you do on the other side of the semi-permeable membrane. If you have this in the case of like a cell, then you'll have the same pressure inside the cell as you have outside the cell. We can also have something that's called a hypotonic. That's where we have a lower osmotic pressure we have a lower osmotic pressure outside the cell than we do inside the cell. Yes. And then hypertonic is where we have a higher osmotic pressure. All right, so here's how I want to explain these. We're going to look at this in terms of what like a red blood cell would look like. So if red blood cells, we have red blood cells in our body, and inside of those cells there are solutes, but there's also water. And then the solution that is around those red blood cells has the same concentration of solutes in it as is inside. And when it has the same concentration inside the cell and outside the cell, as I mentioned before, that is called an isotonic solution. You get the same amount of flow of solvent into the cell as you have going out of the cell, and so you don't build up pressure and it doesn't cause it to shrivel up. However, if you have a hypertonic has a high concentration outside the cell and a low concentration of solute inside the cell. Well, that will cause the solvent to flow out of the cell and it'll cause it to shrivel up. Well, when that happens to a red blood cell, we call that crenation. All right, so that is hypertonic. And then finally, if we have a hypotonic solution where we have low solute concentration outside the cell and high solute concentration inside the cell, we'll have a net flow of solvent into that cell, and it can cause the pressure to build up in the cell so much that it causes it to burst. And when that occurs, we call that hypotonic. All right, so cells hate these last two. Whenever this happens, this causes cell death, and generally that's not what we want to do. So let's look at number 38 on the in-class assignment. I'm sorry, number 8 and then number 73. So 13.8, not 38. All right, so here we've got a balloon that is made of a highly flexible semi-permeable membrane, kind of like a cell wall. If the balloon is completely filled with 0.20 molar, so inside is 0.20 molar, and is submerged in a solution of the same solute that's at 0.10 molar, what term can we use to describe this? Well, since the concentration outside our cell, our balloon, is less than it is inside, we will refer to that as hypotonic. So hypotonic solution. So that is our hypotonic solution. Well, now what we want to do is we want to calculate we want to calculate what the volume of that balloon is going to be. We're going to assume that it's okay for that balloon to swell up as much as it needs to because it is a highly flexible semi-permeable membrane. So initially the volume, this is V1, initial volume is 0.25. We are going to use our dilution equation, M1V1 is equal to M2V2, and we're solving this for V2. So V2 is equal to M1V1 over M2. So M1 is our initial concentration inside, and that initial concentration was 0.20, so 0.20 molal. Our volume 1 is 0.25 liters, so 0.25 liters. And then M2 is going to be the new concentration. And since this is a highly flexible semi-permeable membrane, it will expand. Without bursting, and it will eventually get to the same concentration as outside. So it's going to get to 0.10 molar. Now, I hardly even need to do this calculation, but we'll go ahead and do it. 0.2 times 0.25, and then we'll divide that by 0.1. And of course, we get 0.50 liters. Molarity cancels out. So 0.50 liters. So that object will swell to double its original size. Okay, so now what we want to do is here we've got lysozyme. It's an enzyme, breaks down bacterial cell walls. A solution containing 0.150 grams of this enzyme in 210 milliliters of solution has an osmotic pressure of 0.953 torr at 25 degrees Celsius. What is the molar mass? Now, in solving a problem like this, we want to look at it like this, that the molar mass, normally for molar mass, right, what we would do is we'd go to the periodic table, add up all the carbons, hydrogens, nitrogens, oxygens, and come up with our molar mass. Well, here's the thing, is I don't know what the formula for lysozyme is. It's a really, really big enzyme. So it's many, many thousands of grams per mole. So instead of doing that, we can look at it in a different way, which is if we can just get the mass of our sample and divide by the number of moles of our sample, that will give us the molar mass. So our mass, we do know already at 0.150 grams, but we don't know the number of moles. Well, if we look at this equation, the pi is equal to N over V times RT. We can solve that for N. N is the moles of our solute. So we'll get pi V equals nRT. Again, that looks just like our ideal gas law. We'll solve this for N. N is equal to pi V over RT. All right, now we can just start putting the numbers in. Our osmotic pressure is 0.953 torr. We can deal with that even though R is usually given in liter atmospheres per mole Kelvin. Since it's an atmosphere, we can put a conversion factor in. We'll do that here in just a moment. Our volume here is 210 milliliters. Let's go ahead and convert that to liters and make that 0.2100 liters. The temperature is 25 degrees Celsius, so we're going to put 298 Kelvin. And then R is 0.0821 liter atmospheres per mole Kelvin. If you don't have that memorized, in fact, that's rounded to 3 sig figs. If you don't have that memorized, that's not that big of a deal. That is going to be on the back of our periodic table. So it's a little bit of glare there, 0.0820573338. So you can always look that up on the back of your periodic table when you're going to take a test. All right, and then we've got one last thing here, and that one last thing is we need to convert the atmospheres to torr. So 1 ATM is equal to 760 torr. And just to show you that the units cancel out, so our torr cancels out, ATM cancels out, moles does not cancel out. I didn't mean to cross that out. Kelvin cancels out, liters cancels out. The only thing we're going to be left there is moles. All right, 0.953 times 0.21. All right, divide by 298. Divide by 0.0821, and then divide by 760. All right, and then the number we come up there is 1.076 times 10 to the negative 5th moles. And we don't have that many sig figs. I'll round to 3 sig figs at the end here. So we'll take that number and our 0.150, and we're going to put that in up here. So 0.150 grams, and we'll divide that by 1.076 times 10 to the negative 5 moles. So 0.150 divided by 1.076, second EE negative 5, and that gives us 1.39 times 10 to the 4th grams per mole. So about 14,000 grams per mole. And if you look up the actual molar mass of lysozyme, it's actually a little bit bigger than 14,000, but you get in the right ballpark with this calculation. All right, so that is osmotic pressure, which is the last of our in-class assignment problems, and it's also the last thing having to do with osmotic pressure or colligative properties. But I do want to just ever so briefly look at another topic in chapter 13 before we leave it, and that is talking about colloids. And colloids come in all kinds of different varieties. You can't have a gas colloid, but all the other options where you have a gas that's distributed through a liquid, or a liquid that's distributed through a gas, or liquid and solid and liquid, and there's a whole bunch of different possibilities. And we've got some examples down here of examples that are colloids, but essentially, it's where we've got something that is not like an individual ion or a molecule. It's larger than a typical ion or molecule, but it's too small to be settled out by gravity, and we just refer to that as a colloid. It is a type of it's a sort of the boundary between something that is a solution and something that is a suspension. Suspension, you have fairly large particles like little droplets or something that are suspended through another substance. But a colloid is going to be much smaller than that. Again, bigger than molecules, just regular molecules, but smaller than a suspension. Well, and I just realized that I didn't have this on there. Anyway, so there we go. This is all the stuff I was just saying about colloids. So colloids are these individual. They're too big to be settled. They're too big to be considered molecules, but too small to be settled out by gravity. And then, like I said, here are all the different examples of some colloids. Well, we want to look at something that we refer to as the Tyndall effect. And the Tyndall effect is where our particles that are bigger than the solvent particles, they scatter rays of light. It says solutions do not. I will say solutions actually do scatter some light a little bit, but we'll save that for later. But yes, they will scatter light. So here is a solution. You don't see any scattering. You got this light that's shining through the solution. But if you've got a colloid in there or a suspension in there, it will cause those particles to scatter light. And we can measure how much that light is scattered using special equipment, but we refer to this as the Tyndall effect. So here the glass on the right has a colloid, the one on the left is just a solution, and you can actually see the light scattering, and that is the Tyndall effect. Anytime if you're in a dark room and a little beam of sunlight comes through and you can see all the dust particles that beam of light goes through, well, that's an example of the Tyndall effect. And so anytime there's dust particles, you can see that. If you have smoke particles and the light goes through those smoke particles, that's also the Tyndall effect. Now, when it comes to colloids in biological systems, we can have these large molecules that have very hydrophilic parts on the outsides and very hydrophobic parts on the insides, or sometimes a hydrophilic part on one side and a hydrophobic part on the other. But what that allows us to do is that we can get a big particle like this to pass into an aqueous phase because of these ionic parts or these polar parts that are on the edge. even though it has a big old honking piece of nonpolar part in the middle. And so we can get that to occur. Now, in natural systems, these molecules can be very large, like enzymes and such, proteins of different varieties, so they can be quite large. But we can synthetically do this as well. And so here we can have these colloids that are stabilizing. So if we have a hydrophobic particle that is our colloid, and it has these little ionic bits on the end, we can get these repulsive forces to keep these from joining together. And that allows us to have these hydrophobic parts that are suspended in a hydrophilic part. Well, let me show you an example of a surfactant, which again is a particle that is amphiphilic. It likes polar and nonpolar. And so here is a molecule that's called sodium stearate. Sodium stearate has an ionic portion on the end, and it has a long nonpolar part that is the most of it. Well, if you take a droplet of oil and put some sodium stearate in with it, this long nonpolar part will dissolve in that droplet of oil, but the polar part will stick out on the edge. Well, because that polar part sticks out on the edge, you can get this little boundary where you've got all these little negative charges on the edge of that oil droplet, and you can disperse this in water. So you got the ions, and you can disperse that through the water. And this is what happens if you take oil and water and put some sodium stearate in it. Now, normally, if you take oil and water and you shake them up, at first you'll see all these little droplets of oil floating around, but eventually all the oil will float to the top and the water will sink to the bottom. However, if you put this emulsifying agent in, sodium stearate, you'll find that you'll get these droplets that are stabilized, and so the oil droplets will be evenly distributed throughout that water. It won't be a solution because you can see the droplets, but you will get this stable suspension that's caused by these surfactants. Well, hopefully at this point you realize that sodium stearate is just soap. And so, if you ever get grease on your hands, and if you just try to wash it with just water without using soap, you're never going to get all of that grease off. So instead, what you can do is you can use soap, and warm water helps this process to occur more quickly. But you scrub the oily part with the soap, and what will happen is you can get that the oil to distribute through the aqueous phase, and it will remove the oil from your hands. Pretty cool. Also, it removes oils that are naturally in your hands, so it can dry your skin out. So if you wash your hands all the time, you're probably quite familiar with this. It seems like we're in an age where we wash our hands all the time, and it's very easy for your hands to get dried out because of this. And that's because it's removing some of the oils that are naturally occurring in your skin. So soap is really effective at doing this. Now, of course, the reason why soap is so effective at disinfecting, right, and that's a big deal right now. The reason why the soap is so effective at disinfecting is that those long tails will disrupt the proteins they'll disrupt the fatty layer that's on the outside of either a virus or a bacteria, and disrupt the proteins in those particles. And when it disrupts the proteins, that particle is dead. So if you disrupt the protein of a bacteria, the bacteria dies. If you disrupt the protein on a virus, it will cause the virus to become inactive. So, all right, and that is the end of chapter 13, and also the end of the content for the first exam.